Please, yes. Please, I said yes.
Yeah. So it's my pleasure to introduce our speaker, Ruben Louis from the University of Illinois, who will talk about on construction of differential Z-graded varieties. And it's a joint work with Alexander Hancharuk from Jilin University. So please, Ruben, 1 hour.
Okay, thank you, Alexei, for the invitation. So it's a pleasure for me to give a talk at your seminar. And so today I will talk about this joint work I did with Sasha in Jilin University. So this work is a prolongation of the work previous work done by Kotov, Lowanjangu, and Salnikov on normal form of Z-graded varieties. So I would like to start by the following. See, wait. So it's about graded manifolds, differential graded manifolds. So let's start with the positively graded one. We consider in this paper only splitted NQ manifolds, or splitted Z-graded manifolds, where we're mostly working with the symmetric graded algebra of some vector bundles, graded vector bundle. So a splitted NQ manifold, EQ, is an n-graded manifold, which is of the form where M is the base manifold and the functions is the section of this symmetric algebra of the dual of some vector bundles. And we get it comes together with a homological vector field. That means a graded derivation of that symmetric algebra, so that Q is squared to 0. So there's a very important identification of n-graded G manifold with Lie-finite algebroid. So they are in one correspondence, just like the case of Lie algebroid. So this is valid for Lie-finite algebroid. So you got like one correspondence with n-graded Digi manifolds. So from an algebraic point of view, we can replace the functions on the base M of a manifold by a ring or by an algebra, unital commutative algebra A, and the modules, the module of section of a vector bundle, we can replace that by a projective A module, and then you cook up the same definition very algebraically. Okay, you can do that. So this is what we're gonna do. So we're gonna study those structures in a very algebraic point of view, and then to start with, you should notice the following. So if you have a Lie-finite algebroid, that means it's a homotopy version of Lie algebroids, where instead of having just one vector bundle and then come map and a Lie bracket, so you got a complex of vector bundles, and you don't have a Lie bracket, but you got a two bracket that satisfies Jacobi up to a homotopy, up to a 3 bracket, and so on. So this is what a Lie-finite algebroid is. So in particular, it comes with a 1 bracket, and this bracket defines a complex of vector bundles on the base manifold. And if you have if you take if you take the quotient in the negative degree here by the image of L1, okay, you obtain L2 itself, the second bracket, doesn't satisfy Jacobi, but the Jacobi order is in the image of L1. Okay, so that means if you quotient here, so you got a Lie, something called Lie one-hard algebra over the functions on M. So it's like the algebraic version of Lie algebroids. So this quotient is not a section of a vector bundle. It's not a module section of a vector bundle in general. Okay, that's why we call it Lie algebra. So it's a version of it's an algebraic version of Lie algebra. So it's natural to ask if you have a Lie Reinhardt algebra over functions on M or in general over an algebra A. So can you have a infinity algebra? Okay, so that it is giving us a quotient of this form. So this question was addressed in my previous work in my PhD. So let me first recall what is the definition of a Lie algebra. So as I said, so Lie algebra is an algebraic optimization of the algebra. So by definition, so it's giving as follow. So you need to have an A module M, okay, and A is an algebra, unital algebra A, and M is a module, and then you got a Lie bracket on M, okay, but this bracket is only K linear, K bilinear on M. But if you put a function, so we got something that acts as a derivation, so it's not linear with respect to A. Okay, and there's an income map, a map from M to derivations of A. Okay, just as a Lie algebraic. Okay, except that we got this very algebraically. So we got this Leibniz identity that comes. So you can see that Lie Reinhardt algebras, they are very nice. So, but this M is a very general module, so there's no reason for it to be projective. Okay, and so it's not nice to, if you need to define the connection, you cannot define them on generators. Okay, so and then for differential geometry, it's not so good. So it's really, so we would like to replace that by a version of something that is better in terms of modules, in terms of projective module, right? Since we can have some vector bundles around. And from a result in my PhD, I proved this. So if we have a linear algebra over A, so as a module, M admits always a free resolution or projective resolution. Okay, that encodes all the possible relations and in M and the relations between relations and so on. So in that resolution, you can construct a infinity algebra. I mean, you can construct all the other brackets, okay, and then gives that a structure of infinity algebra, and where the first bracket will be the differential map of that resolution. And this construction, although you made a lot of choice during the construction, but it's unique up to homotopy. Okay, and then this infinity algebra produce M at the end. Okay, it appears exactly as a quotient. M is like if you divide E minus 1 by the image of L1 of E minus 2, you get exactly this M. Okay, so and then this infinity algebra is universal in a categorical sense. So it's a terminal object amongst those that gives M. Okay, and this we lose something because we got much more structure than before. Okay, so we started with just the simplest structure, very simple structure, only with polygonal algebra, but we get a lot of modules around. But what we gain is better now because we have projective modules or free modules, and we can define things on generators now. Okay, so what the theorem really says is that acyclic infinity algebras are the same as Lie Reinhardt algebras. So acyclic means you got infinity algebras whose complex is a resolution is exact. Okay, there's no cohomology. So those leafing dashboards are in one-on-one correspondence, or very equivalent in category sense with the linear algebras. So this result generalizes a geometrical result done by Laval on singular solutions, but they did it only for singular solutions that are solvable in the sense that as a module of vector fields on M. So they admit a projective resolution of this form. Okay, so this result I just presented to you did in my pages is valid for any module without any exception. So although you can get a solution of infinite length or the module may not be finitely generated, but they are free. Okay, yeah. So now we would like to do something more. So we know that for any singular solution that is or Leonard algebra, we can associate a positively graded, or, a leafing algebra which is negatively graded, but as a Q manifold, so it will be only positively graded. But in general, we have a situation where we need to understand the space where the structure is living in. It may not be a smooth manifold anymore, but a quotient by a zero locus of some ideal. And there you have to deal with this quotient and also with vector fields, the infinitesimal bar already too. So there we like to know about the positive part, this Q manifold that give you the singular solution of vector fields. Also, that encodes the space itself or the ideal. Here's a very typical example. So where other kind of Q manifolds appear with negative degrees. Let E be a vector bundle on manifold, and you take a section on that vector bundle, and then just look at the zero locus of that section. So this locus is not free, is not smooth if zero is not a regular value. Okay. So we got this set, this closed subset of E, but you can associate to that zero locus or a kind of Q manifold, but this is very unusual in the sense that it is negatively graded. It is not a NQ manifold as in the definition. Okay, so we got this, and then the Q here is a construction by the section S, and it's equal to 0, and then you got a Q manifold like that, and this encodes the quotient of functions on M by this ideal given by pairing with S, functions obtained by pairing with S, and the zero commodity of that is exactly this. So, but again, we can ask the following question. So what is the universal differential algebra associated with this IS? Or in the sense that you take the one algebra of vector of derivations that preserve IS. Okay, so and then also how this universal Liffinite algebra is related to this negatively graded manifold. Okay, that we associate with S. Okay, so we got like two things that we can associate with the same thing. How to relate them together. Yeah. So this is what we're gonna address here. So one thing you can notice, this negatively graded Q manifold that we associate with the section So although the cohomology of 0 gives you the functions at some point on this 0 locus, because yeah, we can see this quotient as the functions of on the 0 locus, but you may have cohomology in the other degrees. Okay, but we can choose a negatively graded manifold or variety on that locus such that there's no cohomology in higher degrees. So you only have cohomology in degree 0, and this cohomology is exactly functions on IS. And this is called Koszul Tate resolution. Okay. So we're gonna now the question is now can you if you take a Koszul Tate resolution for negative part and then how to relate this negative part and the positive part together. Okay, let me recall what is a Koszul Tate resolution of an ideal of a quotient. So if I is an ideal of an algebra A, so a Koszul Tate resolution of a quotient is a negatively graded key variety. I mean, it's this is a very algebraic version of that. So this are A minus is section is a symmetric algebra of some homogeneous VI. Okay, so those VIs are negatively graded. Okay. So and they are projective modules or free modules. Okay. And then the homology for this is 0 for every degree except the 0 degree. You get exactly this quotient. Okay, this is what we call Koszul Tate resolution of an ideal. So it's a resolution of this quotient as a module, because this quotient is a module. So that means of resolution or operates resolution, but you can take the resolution to have these properties. Okay. And we call it Koszul Tate resolution. And then it's natural to say, okay, how can we compute those resolutions? Okay, so in general, it's hard. It's not easy to compute, or it's very long, not so explicit. But there exists a very explicit construction of Koszul Tate resolution given by trees. Okay, this was done by this works done by Sasha in Yale University, student of Thomas Trouble. So the ingredients to have this Koszul Tate resolution given by trees, so they call it arborescent Koszul Tate resolution because of that. So you need a positive resolution. You start with a positive resolution of this quotient, because as a module it emits a resolution, so you can always have one. But this resolution is not a Koszul Tate one because there's no algebra structure there, so it's not a DG algebra resolution for that. Okay, you start with this, but out of this you can have one. So what you do, you take the symmetric decorated trees of that. Okay, so yeah, there are some signs, symmetric that encode the symmetry in the leaves, and this is how you get this decorated tree, planar tree of that. And then we also need a map from those trees, okay, that projects to M. Okay, so M, we can see M as the decorated tree with single leaf. Okay, and then we got this psi here, and also out of this psi, this map, any map like that, we can construct a derivation of the symmetric algebra of the tree of degree +1, which is defined recursively. So you need to tell what is it on M. Okay, for example, if you apply this map on tree with a single leaf, you got exactly the dv dot sorry, I put M here, but it's V. Okay, if you apply it to a tree with a single leaf, V, you get exactly dv, the differential of the positive resolution of the quotient a by of your quotient a by I. Okay. And then, but if you apply it to trees with two leaves, for example, so you got this expression. If v1, v2 is e minus 1, you just get this expression here. Okay. But if you take v1 in degree less than 1, strictly less than -1, and then you start having the differential d appearing on those leaves, and they will act as derivation, okay, on the leaves. Okay, for example, if you take v2 with negative degree, with degree negative less than 1 to less than -1, so you got another one more expression there. Okay. Okay, so yeah, and then this very explicit thing formula for this psi, but this delta psi doesn't satisfy I mean, it's not squared to 0, okay, in general. Okay, this is just the ingredient to construct this arborescent quadratic resolution. But there's a theorem of Sharuk, which I call Sasha in 2023. This is from his PhD. So it says there is a map. You can always find a map psi of degree +1, so that does this pair, the symmetric algebra of the degraded tree by M is a causal Tate solution. Okay. And then moreover, this resolution comes with homotopy retract. Okay, so we got a homotopy retraction on M. Okay, because MD is a resolution of A over I, the same for the symmetric algebra of the tree. We're giving by n and delta psi, and then you got a retraction between them. And this retraction is very explicit. So I don't want the formula here, okay, but it's given by using operations on the trees and inclusion here, okay, and projection on M. So this is very explicit retraction. And then this multiple retract is very crucial because it allows us to reduce a lot of computations when you compute causal Tate or other things related to that. And this is a very key point in our construction. So it is a very natural question. So if you have causal Tate solution of A over I, right? And then you have a positively graded Q variety. Let me call it E plus Q plus, which is associated to vector fields on a singular space, for example, or in general with a Lie Random algebra over A. So can you find out is that graded Q variety that includes both of them? Okay, so that the positive part of that Q variety is exactly this positively graded Q variety, E plus, and the negative part is exactly the causal Tate thing. And then this will combine both structures together. The answer is yes. And this is a result of Kotov, Lowajango, and Sanikov. So we can always find an extension of the causal Tate solution and the positive graded Q variety into a Z graded one. Okay, but this answer doesn't really tell you how explicit it is, okay, how to construct it directly. So this is the point of the second question here you're asking. So to what extent this Z-graded Q variety E is computable? Okay, so is there an algorithm that terminates in a finite number of steps? Okay, so can we really have some formulas that gives this Q and everything? The answer here is again yes, and this is our work on my joint work with Sasha. So it's on archive. So, but it's yes if we take an arborescent causative solution. Okay, not just a causative solution. Okay, but we are sure that we can reduce the number of computations. So if we have an arborescent one, because the arborescent with causative solution itself is explicit, so there is a very explicit formula for it. Okay, so we can do similar thing in the extension and have a very explicit formula. Okay, so let me state the main result of our paper. So assume that we have what we need. So we need that the killer module differential on A is the projective A module. This assumption we use it here because we need to extend derivations, okay, using projectivity of modules. Because you got something, we get a structure of A on A over an ideal. Sometimes we need to construct a structure over A, and then for that we need to extend derivations on A over the ideal, mod the ideal to A. And then in order to do that, in that situation, we need to use the projectivity of the scalar differential. That's why we added this assumption here, which is true for in the case of smooth manifolds, for example. And this is the situation of the paper of Alex Kotov and Kami Kotov and Salnikov, where this thing is always projective and they can extend things, the version there. So let's say we start with the proper ideal of A. And then we take E plus to be a positively graded Q-variety of A, of this quotient. Okay. And then the VI here, they are modules over A, okay? And then we just take the quotient over A over I. And then we call this E plus. And then assume that we have this an arborescent causal state resolution of this quotient A over I. And then we take together with a map psi from the tree and M. And this map we call it hook is a way to say that there is a relation. It's a way that to say how the M is included is related to the tree. So we get this data, okay, this data, and then you can the result is the following. So there is a Z-graded extension of yeah, there is a typo here again, because in our paper we don't use this. I changed the notation. We call this E plus, this E we call it A. This might call A, and then I was trying to change the notation, and then I forget to change that. And there is anyway, there is a Z-graded extension EQ, such that the homological vector field takes the following form. So the first part is exactly the causative part, okay, the arborescent causative part, delta psi, which we extend. We can because normally this delta psi is defined only on the negative part, but we can always extend it on the whole thing by, let's say, by 0, for example, and then we get something defined the whole thing, okay, but we still call it delta. And we got two other terms, which are nabla alpha and L beta. Okay, so we got this decomposition, and this in this Q here, we already know the causative part, the arborescent causative part, which is very explicit. And this nabla alpha and L alpha, they are given by recursion. Okay, they are defined recursively, and they only depend at some point on alpha and beta. Okay, this alpha and beta thing is in general in practice when you are computing examples, you just need to know them. You just need to compute them. Okay. And then once you have them, so we got Q by recursion. And more precisely, this is a screenshot of our paper because it was hard to write this here directly on the Beamer. So the negative degree one, and the notation is slightly different here because this A is my E here. Okay, so the negative degree component of Q is delta. Okay, is exactly the causative resolution. Okay. Yeah. What I don't see here is on the symmetrical algebra of I mean when you have a z-graded variety or z-graded manifold, okay, you got a lot of different degrees the grading that you can have. Can you have the polynomial degree, and you're gonna have the positive degree, negative degree, okay. And then we can decompose Q with respect to all of these degrees. Okay, so in that situation, we're decomposing Q, the Q E minus, for example, -1 here. When we put this index in parentheses like that, we mean the negative degree. Okay, so which is different as follow. If the degree of the space itself is negative, we just change the sign. So if it is positive, we put 0. Okay, something like that. Okay, it give you the negative degree. So the negative degree, negative one is exactly this this Koszul test. And the negative degree 0 is when you restrict it to the positive part, you get exactly the Q plus, the positively graded thing. Okay. But if A is in the tree, because the total space now, when you put the negative part and the positive part together, is kind of taking out the product of the tree is in the negative degree, and the A plus is in the positive degree. Then you can need to put those together, but we need to take some computation because we may have series that doesn't converge. Okay, so here again, I don't say it, but we consider completion by the negative filtration. You can always do that, and we only consider those series. Okay, and yeah, and then if A is in the tree, so we got a very explicit formula here. Okay, where we already know the nabla alpha 0 given in the first part, right? And then this tau here and P, the projection here, this composition here, it's kind of operation we do have on the tree. Okay, don't worry about that. This is a very explicit thing. And then all the terms here, we already computed them in the previous step. Okay, and this gives you this Q0 applied to something in A in general. Okay, and then for greater for n greater than 0, and then you can look at the negative degree, the component of negative degree n plus 1. So it's really given recursively, okay, using what you know before, and then you can go to the next step. Okay, so it's a very recursive formula, and then this is obtained by perturbation lemma, and then you compute this, and then it's used really the construct. In fact, we have a construction that comes with the arborescent causative resolution, and then it really depends on alpha and beta. Okay, and then we give a special name to alpha beta. We call them retraction residues because they are the one that like kind of reduce really completely the computation. Let me say more about them. So the alpha beta thing, they are k-linear maps. The first one is k-linear, the second one is a-linear. They are degree plus one, okay? And they are defined as following. Okay, so yeah. So in general, you need to, this computation is reduced to the following thing, because every time we are doing this computation, all we use the fundamental thing we use is the projectivity diagram. So we need to find a linear map, knowing we have a surjection and a map, and then we need to extend that, okay, using projectivity of some module, right? So and then every time you need to do this, and do it in the perturbation lemma to construct this Q plus. And then we say that this construction is restricted to some family of modules if we only need to lift to do this operation only for those modules between, for example, here the computations are really reduced, so restricted to this collection of A modules. We need to only construct map between trace I and this module here, M E plus. Okay, so I put this hat over this O plus, O dot, sorry, to say we're really doing this product in the completed asymmetric algebra. Okay, and then we got this constructions, this construction of Q, the extension, Zagordy extension Q is really determined by those lifts, okay? In particular, alpha, beta. Okay, this reaches a great deal the computations we had to make to control this Q. And this is very interesting because this allows us to compute a very explicit example. But we have even more. The situation is even better if we start with a Q a partially graded manifold or partially graded Q manifold, which is defined on the which is already defined on A, not just over A over on A over I, but over A, but preserving I. Okay, for example, if Q plus is already defined on A and it preserves I, okay, that means Q plus of I is included in that module, and which is in general my situation, because we can start with the Reinhardt algebra A, which is defined on a manifold, and then you have a zero locus, and so that this Lagrange algebra or the singular function preserve this ideal, and then you get something on the quotient, right? And then you still want to extend this to the whole space by adding the negative part. But in that situation is better because we can remove the assumption on the scalar differential A over K of A. So we don't need this thing to be projective anymore, because the reason we need this part is to extend some derivations we had, okay? But we already have this because Q plus is already defined on A, so we don't need to extend that derivation from A to E anymore. Okay, so we just need to continue the algorithm for the other things to compute beta or whatever the other components. Okay, we don't need to care about that anymore. Okay, this already simplifies a great part of the computation. Okay, and the second theorem, so we have a very more explicit formula for this Q, for the extension. For example, let me, I put a picture of this formula for you, okay, to show how explicit it can be. And here again, the notation is kind of different, but A plus is what I call E plus here. This A might call A, okay? And it, just as in the arborescent causal Tate resolution of our quotient ideal, so it depends on some map, on some root map, okay, from the tree to M to yeah to M times of functions on E. It's very similar to that. And of course, we got on A plus, we got Q plus. On M, we got an expression like that. That means on tree with only with a single leaf. We got it simplifies like this. And on tree with more than two leaves, or more or equal to two leaves. So we got a very explicit formula for that. Okay. And again, this tau inverse and all of these things are notations of operations on the tree you can make. And we have some degrees convention. So anyway, the point is we have a very explicit expression of the Q. Okay. Yeah, and the proof of that is, yeah, you need to check directly that it squares to zero. Okay, and this is an extension of the causal Tate part and the negative part and the positive part. Okay, this really give you very more explicit one, just because the Q plus was already defined on A plus, and the computations are completely even more restricted. Okay, we got to do less computation. Okay, so let me give an example of all of that. So we have computed several examples in different situation. But here I just present one of them. I could have presented more, but yeah. So for example, we computed the example of vector fields of the that vanish on a subspace. Okay, and we got a very nice form for the extension too. Okay. Okay, let me start with this one. I think this one is nice too. So you take A to be the polynomial algebra with two variables, x and y, and then take I to be the ideal given by this x squared, xy, and y squared. And then you want to look at this Lie one algebra of derivations x that preserve this ideal. Okay, so if we compute this, so this Lie one algebra is spanned by this vector fields. Okay, x dx, y dx, and y dy, and x dy, and so on. Okay, so we got these four vector fields, and so using my the first theorem I presented here in my PhD, so we can construct, there's a Lie algebra attached to this. To do that, we need to take a free resolution, okay, of M of this module. But in that case, the resolution is very short. So we got it's of length 2, okay, and then we can compute easily what is the. So that means there is a Lie algebra that gives you this module. So L is giving the income map here. Rho is giving by that. So we send E1 to those generators. And then the map L is giving by this expression here. And it encodes the relations between the generators of the kernel of Rho, okay, of the income map. Or the relation between the generators of this ideal I at some point. Okay, so here U, V are the best element of that. So there's a little algebra that we can compute very explicit here, very explicitly. So it corresponds to, if you dualize it, it gives you a Q variety, okay? Because you can always dualize it in that case. And then the very expression of this Q plus. Okay, if we were by psi 1 and psi 2 and psi 3, the basis of the dual, because it does everything. It gives you a Q manifold or Q variety, and in the Q plus is given by this expression. Okay. And this first part is the income map, either L2 and L and L3. Okay. Okay, so we have this Q plus, very explicit. And what is the negative part? To consult the negative part, I mean the consulted resolution for A over I. And here again it's not so long, so it's very simple. So we should start with a fully or projective resolution of this A over I as a module. So we got something of length 2 again. So very more specifically, this map D is giving as follows. So if you take pi 1, pi 2, pi 3 to be generators of m minus 1 and pi bar, generators of e minus 2, and then the D is giving as following. Okay. Okay, and then this is the negative part. This is just the resolution. So, but the causality, it completely determined by this psi map, this hook map, right? So you just need to know the hook map, and then you got this very explicit. We can expand it. So, and then if you just need to know it, since you don't have a lot of degree of freedom, so you just need to compute all of the psi on those map on those trees with two leaves. Okay, so if you apply it, for example, on pi 1 over pi 2, you got x pi and so on. Okay. And then it is 0 in all the other cases. Okay, and then this determines the causality part, the arborescent causality resolution. Okay. And then what is the total Z-graded description of this? You need to know it on the tree. You need to know it on M. Okay, we already know it on E plus, right? So, and then here you got a very explicit expression for that. So I don't want all the details. For example, if you evaluate it on the tree with three leaves like that or this form, so this Q applied to these three leaves is given by something by some of those terms here. So for example, A is on the form is the tree with two leaves, and you multiply by pi. Okay, and then you subtract the tree with three leaves like that. Okay. So again, it gives you something very explicit. And for example, the components B is giving is where D is acting as a derivation on the leaves. Okay. So since we know those generators on E minus 1, M minus 2, and M minus 1, they are related by D, right? And then yeah, the second part, the B term is giving as following. So yeah, to tell you get a very explicit formula, just because we have this tree that solves all this arborescent causal state. And then when you put it together using this formula, because we are in the situation where the Q plus is already defined on A. Okay. That means we don't need to use the projectivity of anything of this Kähler differential. Okay. And then we have simplified a great deal of thing, and then we got a very explicit formula. So we just need to use so every time here we just need to compute this alpha, beta, which we call the residues of this causative residues of this construction. And once we have them, and then use this very recursive formula, and then we can determine very explicitly this extension. Okay, yeah, and here this is the terms where the acts on the leaves. Okay. And that's yeah, I wanted to like just give these two terms just to show you how it works. Okay, I think that's all. So for my talk, thank you for your attention. And these are the references. So if you like to have to see more examples and in details about this construction, so please I can go to take a look at this paper where we have a lot of examples, because this paper was mostly about having a very explicit construction of this extension, and then to show that we can have very explicit example by using the arborescent when we have the arborescent quality resolution. Thank you for your attention.
Thank you, Ruben, for the question. Now, questions?
Yes. Hi, Ruben. I have a
Hi.
question. Can you go back to the expression of your Q in the example? Your Q plus, I guess. Okay. So just for me, just check if I'm understanding correctly. I mean, the first few terms are kind of the generators of this Lie hard algebra, right? The ones
Yeah.
with they have the
Yeah,
size.
yeah, those, yeah. This is the income map, the first three terms.
Yes.
4 terms.
So like
the first 4 terms, yeah.
so the next ones are probably like the brackets between these generators. Is that right? Or
The next one, you mean the eta one?
yeah, the etas ones. These
Yeah,
are
these are given by the second, the two bracket, I think. Yeah. Sorry.
okay. So each
Sorry. This is the, yeah, the 1 hour bracket. You got the 1 hour bracket. You got the income map. You got the 1 hour bracket. Okay, the second one. And then and then we got the 2 hour bracket. Xi give you the 2 hour bracket. And then the eta squared here give you the 3 hour bracket.
mhm. So the
Yeah.
eta 1 and 2, they are like brackets. I mean brackets like Lie brackets of the generators, or no?
The etas, they are generators on the dual.
Okay.
Yeah, because eta
Okay.
is the basis of V2, right? And the xi's are basis of V1. Okay. So when you dualize, the coefficient is exactly the coefficient in the expansion of your, for example, let me go back here. For example, L1, L applies to U is given by that, and L applies to V is given by that. This is the 1 hour bracket, right? So we got this coefficient here. If you dualize it, you see exactly the same coefficient appears here. You just need to change. See, before it was like X E2 negative Y E1. Here is X partial E2 negative Y partial E1. So it's like the same coefficient here. And then you just replace that you just take the dual basis of your previous base, and then you multiply it by this for degree reasons, because you need to have something of degree +1.
Oh, okay. Okay.
And then do the same
Thank
thing for
you.
the other coefficients. Yeah. It's like
Okay, great. Thank you.
yeah, it's literally the dual of those brackets. So you got the same exact coefficients, but you just need to replace the basis by dual, and that's it.
Ah, okay. Okay, but it's the bracket. Okay.
Yeah.
It's okay. Thank you. Thank you.
Thank you. Other questions? Okay, maybe let me ask you kind of general one. So there is a tree construction for the Koszul-Tate resolution, which simplify the procedure of computing the Koszul-Tate resolution. and makes it computable in a sense. But can you summarize how it helps to for the homological perturbation theorem? Because homological perturbation works for every Koszul-Tate resolution, right? So the idea is pretty much the same. But how does the tree construction help to construct also the other part, the positive part?
Okay, the thing, I mean, as you said, this is exactly the same lemma we use, the thing you use to construct it, the perturbation lemma here. So how it helps? So you do the same thing it will do, except that you first make a choice, okay? Of because you take the negative degree expansion, right? And then every time you need to construct what is the degree 0,
Right.
degree -1, and degree 1, and so on. And then every time you have them, and then you do this cohomology thing, and then
Yes,
you
right.
use exactness of the Koszul Tate, and you construct
Yes, precisely right.
Yeah, and then when you first make a choice, and this choice is very, very abstract. So there's a lot of components to compute in there,
Exactly, right.
right? And this is where the arborescent Koszul Tate plays a role, because in the arborescent Koszul Tate, we have this homotopy retract. And this homotopy retract is very explicit. So it allows you, and then using this homotopy retract, and then we can have another choice. We can make another choice that reduces the computation, because and in some part you throw them in the homotopy retract thing, and then you just need to compute a few things. That's why the computation is reduced.
So it gives also the choice, not only it gives the choice of the representatives, right?
Yeah, I mean, it gives you a choice, another choice that depends on less parameters, on less computation.
Okay.
And then but you keep doing the same thing you used to do, but every choice you make, you say, okay, you can make another one which is better and that has less computation, because most of them is in the homotopy retract. Yeah.
Right. Thank you.
Sure.
Other questions? Okay, if not, I think Sasha is here. Sasha, do you want to ask any question? Okay. Probably he knows the answer.
Not allowed to ask a question.
Okay, right. But you can in principle, right? Because you are also a participant. Okay, so if there are no questions, let us speak the speaker again for this interesting talk.